Okay, in this video we're going to look at how we do projectile motion calculations. I'm going to apologise in advance, this one is a bit long. I try not to make the videos this long, but I really wanted to go through in the same video the theory that we use to do the calculations, and then straight away in the same video doing some example calculations. So this one runs to probably about 40 minutes or so. But hopefully you'll find this useful and helpful. Let's get into it. Okay, so in these first couple of slides, we're going to talk about, if you like, the theory of how we do projectile motion calculations. It might be a little bit confusing, but I think it's important to understand. And then I'll go through some examples in the next two slides, which will hopefully make things make sense. So, in the first scenario here, calculate the time of flight when a projectile is launched horizontally. So we can think here of a ball rolling off a table, say. It's got a horizontal velocity. Initially, there is no vertical velocity. So we can think that the initial vertical velocity is equal to 0. Its velocity is in a horizontal direction. Now, gravity acts in a vertical direction, so it's really only the vertical velocity that's going to determine the time of flight, and the vertical displacement, SV, that I've labelled here. So I'll write the formula out and then show how we can use it. We can use this formula S equals V, and in this case we're interested in, let's say, because we're interested in the vertical component, times time plus a half times the acceleration times time squared. Now, the initial vertical velocity is 0, so this whole term here will be equal to 0, so we can ignore that. So this, if you like, simplifies to say SV, the vertical displacement, equals a half times the acceleration times time squared. But as we said here, we want to know the time of flight of the projectile. So we've got to rearrange this formula. So we've got a half here, so to get rid of the half, we times both sides by 2. That cancels. We've got an a on this side we want to get rid of, so we both sides by a. And we've got a t squared here, and the way to get rid of a t squared is to take the square root of both sides. Sorry, I'm overlapping here. So what we get left with is, oops, wrong colour. I was trying to stay there in black. The square root of 2 times SV on A equals T. So for a projectile that's launched horizontally, that's how we can determine the time of flight. I don't expect you to remember that formula. What I expect you to be able to do is construct a diagram, think about the formulas that apply and where they apply, the vertical component, and then work out that relationship from there. Although if you do it a number of times, you do tend to start to remember these relationships if you put the practice in. So that's the first scenario. The second scenario, calculate the time of flight and maximum height for a projectile when launch height is the same as landing height. I think I forget to say this before, but this, and I'll put a link in the lesson on Teams, this PhET simulation is a really, really good way to play around with these things and see what's happening. I've got this picture out of there which shows a projectile launched from where the launch height equals the landing height and how we go about time of flight. But yeah, strongly encourage you to muck around with that simulator, and I will show you some of that in class to get a feel for what's happening with these calculations. So in this case here, what we need to think about is the, what colour's going to work best there? Let's draw on this diagram. We're initially launching this here, so that's our initial velocity. And basically, again, we need to resolve it into its horizontal We've got 45-degree angle there. That's, you can just pick that up on the diagram. So we need to work out the vertical and the horizontal components. And I think I've just written over, but I think it said 15 meters per second there was the velocity. So to calculate the time of flight, again, it's the vertical component. It's going to go up, and vertical, just think about the vertical is going to get slowed because gravity acts against the vertical. At the highest point, it's going to equal 0. The vertical velocity will 0, and then as it falls, it will accelerate at the same rate it slowed down. So basically, it'll take the same amount of time to come down as it will take to go up. So I often sort of divide this problem into those two parts. We have then, when we think about that the initial, well, firstly we've got to work out the vertical and the horizontal component. So VV equals V sine theta. And we're actually not going to use the horizontal component in this part, but we will actually need to work it out. So let's put that in there. Equals V cos theta. Then what we're working out here, if you like, is the initial. So we'll put in a 0. The horizontal will be constant, so I'm not going to put 0. The horizontal, no force in the horizontal, so that won't change. And what we know here is the final vertical velocity. So this is, if you like, at the highest point. Will be equal to, hang on, I'm just going to move my pen out of the way, will be equal to 0, because at that moment, at the top, it will stop. So how do we work out the time of flight from that? Well, if we use the formulas which come off our formula sheet, we probably would start off with this formula here, which says V, if you like, our final velocity at our highest point, will equal the vertical initial velocity plus A times T. We want to get T on its own. So what colour shall I use here? We're going to have to get rid of the VV's VV0, the initial vertical velocity. Take that from both sides, so that cancels. And then we've got an A here, so we're going to divide by A. And we're going to also remember that V, the final vertical velocity, so the vertical velocity, if you like it, at this highest point up here, is going to be equal to 0. So after we do that, we simplify that all down, and we get left with minus VV0, so minus the initial vertical velocity, divided by the acceleration, will equal the time of flight. Remember though, that's not the time of flight, that's the time to the max height. Sorry, I just got a funny thing going on here. That's time to the max height. So to get the total time of flight, use TOF for time of flight is equal to 2 times T that we just calculated there. So just to go from that step, we've got to times that by 2, because the time it takes to go up is equal to the same time that it takes to go down. If we want to find out the vertical displacement, and we might just flick to another colour here. So what's this maximum vertical displacement? SV. Basically we need to use the displacement formula. SV equals VV times T plus a half AT squared. And that's, sorry, V0 times T, so the initial vertical velocity. And if we basically plug all that in to that formula, we know the initial vertical velocity from, sorry, I'll use the pointer. We know that value from there. We know the time to get to the maximum height. This was this time here that we calculated. We know the acceleration, which is always downwards at, so that's always, oops, go back to a pen. That's always 9.8 meters per second, and it's in the opposite direction to the velocity. So if we say the velocity is positive, that's going to be negative. So basically we can use that formula and calculate the vertical displacement by looking at the vertical velocity and the time to reach that maximum height. So that's ticked off. Calculate the time of flight and maximum height for a projectile where the launch height is the same as the landing height. Finally, actually before I say that, we could also have used this formula here, which is that V squared equals V0 squared plus 2AS, and just worried about that in the vertical, because we know the initial vertical velocity, we know the final vertical velocity was 0. The initial vertical velocity we worked out up here, and we know the acceleration is equal to 9.8 meters per second. So we could rearrange that formula and also work out the vertical displacement, whereas with that first formula we don't need to rearrange, so that's probably the slight advantage of that. So yeah, two ways though you can work that out. Finally, calculate the horizontal range of a projectile when it is launched horizontally, or when the launch height is the same as the landing height, or the time of flight is given. So what we're talking about is either in this case here, calculate horizontal displacement, or in this case here, calculate the horizontal displacement from here to here. And in all cases, that is fairly simple. All we need to do is so we're talking about this one here now. We basically need to know the horizontal displacement is equal to the horizontal component of the velocity times by time. So in this case here, the time of flight we've worked out, the horizontal component is equal to the initial velocity because it was going horizontally. In this case here, we would use the horizontal component times it by the time of flight. So that should be a fairly easy calculation. The final point, determine the velocity of a projectile at any time using trigonemic calculations or vector addition. I'll quickly show you that again, but that was basically what I went through. Basically at the end of the last video, where you basically have, it's probably in a sense, I guess, the opposite of what we did at the end of last video. Let me just undo that. Strictly speaking, I probably should do it this way. If we are able to work out at any instant the horizontal component of the velocity, and we know the vertical component of the velocity, we can therefore work out the total velocity by adding the horizontal and vertical component vectorially. So to get the length of that line or the magnitude of that vector, we use Pythagoras. V equals the square root of VH plus VH squared plus VV squared, which as I said, I've already talked about this, but I'll put it on this slide as well for completeness. And then if we want to work out that angle here in here, we can either use what we all know all three sides of the triangle. So we can either use sine, cosine, or tan to work out the that angle so we can work out the direction of the projectile with respect to the ground. As I said, I probably repeated myself in the previous video there, but that is theoretically how we calculate all those various things that are listed in the subject outline down here. There's still a couple more that we need to look at in the next slide, and then we'll get into some example calculations. Okay, in these next parts, the first thing we need to do is explain qualitatively, which means without numbers, just in words, that the maximum range occurs at a launch angle of 45 degrees for projectiles that land at the same height from which they were launched. So as the launch angle increases, we've got two competing effects happening. Firstly, the vertical velocity, as we increase the angle, increases. That increases the time of flight. Now the range, which is the horizontal displacement, is equal to the horizontal component of the velocity times by time. So if time is increasing, that's going to help assist the range increase. But also, as the launch angle is increasing, the horizontal component of the velocity is decreasing. And so if this is decreasing, that's going to cause a decrease in the range. So you've got these two competing effects, and basically that optimum trade-off, at least in terms of range, occurs at 45 degrees. Okay, again with the next point, describe the relationship between the launch angles that result in the same range. Go and play with this one on that PhET simulation, but basically we get equal range at angles that are theta and 90 minus theta. What does I mean by that? If you haven't done a lot of maths, that might be a bit confusing. Basically, that means that we get equal range at 0 and 90. And then again, let's do it, say 15 and 90 minus 15, which is 75 degrees. And at 30 degrees and 60 degrees. And at 45 degrees, and well, 45 degrees, obviously, if the launch angle is the same, the range should be the same. And then if we keep going at 60 degrees and at, well, we've already covered this because in a sense, 60 and 30 is the same as 30 and 60 and so on. So what I encourage you to do, and I'll probably show you this in class to make sure you do it, is go and play with that PhET simulator and see what happens to the range and see the lines on the diagram when the launch angles are equal to theta and 90 minus theta. I don't even remember if that's complementary angles, but I think they add up to 180 degrees, or I can't remember exactly, but theta and 90 minus theta, I think when you see it on a picture, it will make sense. Finally, we need to be able to describe and explain the effect of launch height, speed, and angle on the time of flight and the maximum range of the projectile. And I think that sort of probably all hopefully just makes sense from what we've looked at. Obviously, if launch height, oops, wrong button, launch height increases, then range will increase. Again, just an up arrow as a shorthand for increase. If launch speed, oops, spelling mistake there. If launch speed increases, range will increase, providing there is at least some launch angle. And angle, on the angle, if we, that's a bit more complex because if launch angle, oops, did the same thing again. If launch angle increases, firstly, time of flight, because the vertical component of the velocity will increase, so time of flight will increase, but the range is a little bit more complex, and in a sense what happens with the range has already been covered let's just say C above. Because as launch angle increases, we've already explained through that bit up there. So, you know, this is addressing, I guess, some of those explain type questions that we will get again about projectile motion. The previous one was probably more about the calculation question. Hopefully, to make this a bit clearer, in the next two slides, I'm going to go through an example calculation, and hopefully that really helps you understand what's going on, if you don't already. Okay, let's have a look at a real example question. And this question here is actually a picture of my son Russell, I believe, and we're on the 4th hole at the Roxby Downs golf course. And you can see he's about to hit that golf ball. And for the sake of this question, we are going to say that he is going to hit that golf ball with an initial velocity of 52 meters per second at an angle here, launch angle, let's call that, theta there, of 15 degrees. And the first thing we need to do is calculate the initial vertical velocity. So the initial vertical velocity, we can go v, and we'll show it's the initial by putting a 0 there, equals v sine theta. Now, always important, this is a place I see a lot of people lose marks in exam. Make sure that we substitute into that formula. So that equals V is equal to 52 times by sine of 15. And that gives us an initial vertical velocity of 13.46 meters per second. Then we look at the initial horizontal velocity. VH0 equals V cos theta. Substitute in and show that substitution. Sorry, it's cosine that time. Cosine of 15 degrees. And we get there 50.23 meters per second. Often that's the first question in the exam. Do 2 of those substitutions, get the answer. Then calculate the speed of the ball 1 second after launch. So notice it says speed here, so we don't need to worry about the direction. We just need to worry about the magnitude, the scalar quantity, the magnitude. So to do that, we have to work out, well, what is going to be the horizontal velocity and what's going to be the vertical velocity after 1 second. No forces act in the horizontal direction, so that stays constant. So the horizontal component of the velocity after 1 second will still be equal to 50.23 meters per second. However, gravity is acting in the vertical direction and it's slowing the ball down as it goes up. So it's acting in the opposite direction. It's negative. The acceleration due to gravity is 9.8 and it'll be negative 9.8 because it's downwards. So V vertical will equal V vertical initial plus acceleration times time. When we substitute in there, we get 13.46, and it's plus a minus, and a plus and a minus make a minus, so minus 9.8 times by 1.0 seconds, and that is equal to 3.66 meters per second. So then, to work out the total vertical velocity, we need to add those two things back together. So we have got, let's draw it here, I might just use this different colour here, VH equals 50.23, VV will equal 3.66. We add them together vectorially. So we use basically our Pythagoras here, and we get v, the total velocity after 1.0 seconds, we can show that is going to be equal to the square root of 50.23 squared plus 3.66 squared, which is equal to 50.36 meters per second. Now, oops, just running out of space there. Strictly speaking, we're only given two significant figures in the question, so that answer should only be two significant figures. So it should be 50 meters per second if we were being really fussy. Okay. Then we need to calculate the time of flight of the ball. So when we're interested in time of flight, we're really only interested in the vertical component of the velocity. And we can, I'll probably strictly speaking start with the formula v equals v0 plus at, and we want to rearrange that. So we take v0 from both sides, and we're going to divide by a from both sides. So we get left with that the time of flight is equal to v minus v0 over a. Now, the initial, we're dealing here with just the vertical, so the vertical, and I should make that vv0, the initial vertical velocity. Now, I always like to do this and think about just on the way up. So what's the velocity at the highest point? That will be 0. Then it will basically take just as long to fall as it does to go up. So when we substitute in there, if we just do this for the upwards, we get 0 minus 13.46 divided by minus 9.8, because gravity is acting in the opposite direction to velocity, and so we're saying that's negative. So that gives us 1.37 seconds, but we've got to times that by 2 because it takes the same amount of time to come down as it does to go up, and that gives us 2.75 seconds as the total time of flight. Then, to calculate the range of the ball, we basically, almost the most simple part, the range is the horizontal displacement. That's equal to the horizontal velocity, which is constant because there's no force acting in the horizontal. We're ignoring air resistance in this question, times by the time of flight. Again, make sure you substitute in. We get 50.23 times 2.75, which gives us a range of 130, when we round that all off, 138 metres. Determine whether the ball went in the hole. I'm going to let you see if you can find out how long is the fourth hole at Roxby Downs Golf Course, and find out whether the ball actually went in the hole or not. Anyway, only if you're really keen to. I'm not really fussed if you don't do that last bit. It's just there for a bit of fun. Okay, so hopefully that demonstrates a lot of the skills that we need to do for projectile motion calculations. This is one where we're assuming that launch height equals landing height. We're assuming it's a flat hole. I'm going to go through one more in the next slide. Okay, in this question we've got a ball kicked horizontally off a cliff 20 metres above sea level with an initial speed of 10 metres per second. Calculate the time of flight and hence the range of the ball. Now, I've drawn a diagram here. If you're never sure where to start a question, drawing a diagram is often a really useful thing to do. So, the first thing that we need to do here is work out the time of flight. And we know, if you like, the information that we know is we know that the vertical displacement is 20 metres, and we know that the horizontal velocity initially is 10 metres per second, and because it's horizontal there is no vertical component, so the initial vertical component of velocity is 0 metres per second. And given all that information, and we know that the acceleration is equal to 9.8 metres per second downwards. Maybe that just reminds us about direction, although direction's not so crucial with this one because the ball's only falling. So, what formula will link those all together? And I went through that in one of the earlier videos. Or was it the earlier part of this video? I lose track. That is basically, we can use this formula SV equals VV, and this VV, well, the initial velocity, in this case the vertical component, times by the time, plus a half, times A times T squared. So we know the vertical displacement. We know that the initial vertical velocity is 0, so we can just ignore that whole term. And we know the acceleration, so we've only got one unknown, the time, but we do need to rearrange this formula to work that out. So we want to get rid of the 2 on the bottom here. So we times both sides by 2, and then that cancels. We want to get rid of the A here, so we divide by A on both sides, and the A's cancel there. And to get rid of the square root, the t squared, we take the square root of both sides. So we get left with t equals the square root of 2sv over a. Show the substitution. 2 times 20 divided by acceleration, which is 9.8, is equal to, put that in the calculator, and we get that's equal to 2.02 seconds. And then we want to work out the range, which is the horizontal displacement. So SH, the range. So SH is equal to VH, that's constant. So it's the same as the initial horizontal velocity times by time, and we get that that's equal to, 10 from the question up here, VH, times by 2.02, which is equal to 20.2 metres. Again, the question's only to 2 significant figures, so strictly speaking, we should round that off to 20 metres. So that's how we've worked out the range. So now I've gone through 2 examples of projectile motion calculations. Hopefully you're feeling enough confidence to at least have a go at some of your own, and hopefully to be able to do some of your own successfully. Cheers. In the next video, we'll go through air resistance.